And this is 9-1, the alpha lesson. So we're going to start with the PDF and then go to the Google Slides. So this is the problem from the end of 9-1. Now think about what this is saying. To which of the following numbers does this series converge? So we talked about this a little bit in chapter 8. We did just section 8.1. If the terms are separated by a comma, it is a sequence. If the terms are separated by an addition or subtraction sign, it is a series. So this says you have these numbers, 1 plus 1/3 plus 1/9 plus 1/27. Where is that going? To what number? Now here's what's interesting to you, I hope. This series goes on forever. Plus, ... Say it converges means there's a sum to that series. And if you say, okay, well, wait a minute, you keep adding stuff to it, it's just getting larger and larger without bound. This series isn't. Like if I add up the digits, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, and I pull a Gauss, yes? And I'm going to have the first 100 digits, which equals what? Correct, 5,050. That series diverges. It just gets larger without bound. This one is an example of something that doesn't, that converges. So, the sum, it's geometric. What does it mean to be geometric? Well, we did this in chapter 8. It means you have a constant ratio. You're multiplying by the same amount. What is the ratio in that problem? 1/3, correct. Because you have 1, and you multiply that by 1/3, and you get 1/3. And you multiply that by 1/3, and you get 1/9, and so on. That is an infinite geometric series. Now, how about the sum? If it's finite, here is the algorithm for a finite geometric series. If it's infinite, that's the algorithm. Now, I wrote this on the board. We did chapter 8, but I don't expect you to remember that. You don't need to write this down. You just need to follow it. Here's the derivation. Sigma, the sum. G sub 1 means the first term of the geometric series. And R is the constant ratio. S sub n is the sum. So my first term is G sub 1. Yes, the first term. And that'll be multiplied by R to the 0 power, which is 1. Meaning you didn't multiply by R yet. Then the next term would be G sub 1 times R to the first. And the last term would be G sub 1 times R to the n, take away 1. Because you're multiplying by R in between the terms. So with the second term, you multiply by R once. For the 10th term, you multiply by R 9 times. So for the nth term, you multiply by R and take away 1 times. And in order to get the sum, what we do is we say, multiply this entire line by R. So if we multiply the whole line by R, we distribute an R over every term. And then I just moved everything one spot to the right. There's a 1-to-1 correspondence between these terms. But I moved everything 1 to the right. Why? Because if you subtract these vertically, all the middle terms will add to 0. And just give you the first term. Now, watch this. Subtract that term. So even though it's plus, you're subtracting it. Subtract that term. The greatest common factor on the right, I'm sorry, the left is the sum. Factor that out. On the right, G sub 1. Divide by 1, take away R, and you have this algorithm, which is here. For a finite geometric series, that gives you the sum. Now, here's what's interesting. If it's infinite, it never ends, we can get the sum. Because look what happens. If R is less than 1, now we can only do this if R is less than 1, the constant ratio. If R is less than 1, when you multiply it by itself, it keeps getting smaller. It's a limit. 1/2 times 1/2 times 1/2. It's getting smaller and smaller. It's going to 0. In that example, 1/3 times 1/3 times 1/3 is getting smaller. So if it's infinite, R to the end is going to 0. So you would just have 1 times G sub 1, and that would be the sum. For an infinite geometric series. So we're going to go to the PowerPoint and then come back to the PDF. What's this? Zeno's paradox. Remember when you were in middle school and Bezique or somebody teased you and said, how far is it to the door? And you said, do you understand, to get to the door, you have to walk halfway there first? And after I walked halfway, if I paused, then I have to walk halfway again? And then I pause and I walk halfway again, you'd never get to the door. That's Zeno's paradox. Yes? Except what? This is showing you that if you walked halfway and then another half, which would be a quarter, then as long as you don't stop walking, you'll fill the square in. What is that? That is an infinite geometric series with a constant ratio. First term is 1/2, and the constant ratio is 1/2. So what was the algorithm? The algorithm was first term over 1, take away the constant ratio. So you would have 1/2 over 1, take away 1/2, which equaled 1. Except what? That means you this is the abstract concept. You never stop filling that in. It's infinite. That's a little bit of an intellectual challenge you have to think about. The reason that that thing is 1 is because we agree that we will never stop adding terms. Many series do not converge. Most of them don't. The ones that converge are special. That's the ones we're interested in. So look what they got here. That's the harmonic series. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. Now what do you notice? They keep adding a smaller amount each time. Yes? But it's still going to this through the ceiling. It's still growing without bound. What do you notice about the difference between this harmonic and that problem? Eddie? Correct. It's not geometric. So for something to converge, now, ready? For today, we say it has to be geometric. It doesn't have to be geometric. But the terms certainly have to be getting smaller. And those terms are getting smaller, but that series diverges, barely. Barely, but it does diverge. So let's get, our mind around this. This is saying first term, second term, third term, fourth term, and the way they write this, you have to read the vernacular here, is the sigma start at 1, go to infinity of a sub k. So what does that mean? put 1 in for k, then 2, these are all integers, 3, 4, 5, and those would be the terms, and you never stop. Okay? What do you, this is your H chart. So what does this look like? The H chart for the problem that they showed you would be this. The first term, n, g sub n, and the sum. The first term was 1 on that question at the back of the book. Then the next term was 1/3. And the sum, partial sum, would be 4/3. And the next term was 1/9. So what is this? That's 12 ninths plus 1/9 is 13 ninths. Now, how are we getting these numbers? You can either add vertically or add diagonally. In the right-hand column of the H chart, that's why the H chart is important. See, it'll help you with derivatives. That's where you put the derivatives, in the third column. That's where you put the list of partial sums, in the third column of the H chart. And what do you have here? This is a Roman letter S for sum. That's the Greek letter S for sum. So we're just telling you if it has a limit. So we don't really know what that means yet. Well, we know what a limit means. We don't know in the context of this. So we already did this. Where the first term is A. What do we call it? We call it G sub 1. That makes more sense to me. The geometric series identified with the G sub 1. They're calling it A, whatever. It converges. Our first term was G sub 1. They're calling it A. If the absolute value of R is less than 1, it'll converge. If you multiply by a number less than 1, and if it's an infinite geometric series, it will converge. If the number you multiply is 1 or higher, it will diverge. Converge is good, diverge not so much. Now, the absolute value of R is less than 1. We know how to do this. Get rid of the absolute value symbol. So that means it goes from -1 to 1. Open interval. Parentheses, not brackets. That's the interval of convergence. Meaning what? We could have multiplied by a -1/3 in that question that you started with, and it would converge. Because -1/3 is between -1 and 1, exclusive of the endpoints. So we know what this is. Ready? This is 3/10 repeating. So what do people do? Well, the shortcut for this is I've got 0.3 repeating. And I call that, I don't know, K. So I count the number of places that repeat. 1 place repeats. So I multiply this by 10 to the first. Subtract 9K equals, everything to the right of the decimal point adds a 0. So K equals 1/3. Yeah, you knew that, right? And we showed you that that's why 0.9 repeating equals 1. You sure about that? It does. 0.9 repeating equals 1. So now what? Well, here's a different way to look at it. Think about this. It's an infinite geometric series. So I would say the first term is 3/10. 1 subtract the constant multiplier would be 1 subtract 1/10. And 3/10 subtract, I'm sorry, 1 subtract 1/10 is 9/10. And 3/10, anywhere you want, Gina. 3/10 divided by 9/10. No, there's magnets. Ready? They're behind that, the yellow banner. So this would give you 3/10 over 9/10. The tenths would reduce out. 3/9 equals 1/3. The red is a shortcut. The blue uses the algorithm. It's still taking you to the same place. Certainly, Gina. That's doing the problem the long way. The first term divided by 1, subtract the constant multiplier. You only do this under 2 conditions. That it is geometric and the constant multiplier is less than 1. The absolute value of it's less than 1. If you're multiplying, if it's geometric and you're doubling it, you're wasting your time, because that would diverge. Oh, what do you notice here? Yeah, or it's negative. That's fine. That's the partial sum. That's on the PDF. Why? Well, I showed you that expansion. But this thing, this factor has a value if it's a partial sum, because you're not going to infinity. So the number in the parentheses in the numerator would be finite. It wouldn't be 1 subtract 0. But that's how we showed you to get this expansion from the finite expansion. All right, so now we're going to make this a little more complicated. All of that is pre-calc. So if x is less than 1, you would get this. First term is 1, constant multiplier is x. So where's this going? First term divided by 1, subtract the constant multiplier. If and only if the absolute value of x is less than 1. Except here's where this is going. Ready? The left side is an infinite series. The right side of the equal sign is a function. So if you want to estimate the value of the right side by using the left side, because we're estimating it now, then the more terms you use, the closer your approximation will be. Well, it's infinite. Correct. But if we were interested in the partial sum, then the left side will estimate the right side depending on how many terms we put on the left side. Power series. Now, what does a power series mean? It means the independent variable is in the base. It's like a power function. Ready? Do you understand the difference between this? Y equals 2 to the x, y equals x squared. Okay? This is a power function. That's an exponential function. If you're in statistics, we have to do transformations. Here's what you're looking for. If it's a power function, the exponent is an integer. Now, this looks kind of fouled up. I don't really, this looks really confusing. You're not really used to this font. All they're saying is this. The first term is 0. You're going from 0 to infinity. So you would have c sub 0, which is the initial term. We can start at the 0 term of the first term. C sub 0 times n to the 0. Anything to 0 power is 1. So you get c sub 0. Then you go to the next integer. N's an integer. You go to 1. C to the first, x to the first. And you go to the right without bound. Then from here to here, what did they do? Oh, please. William? To do what? To move everything to the right, correct. So they did the opposite. So they replaced x with x subtract a, which moves everything a units to the right. When they say left or right, like if a were negative, you subtracted a negative, that would be moving it to the left. Yes, I see that. Because what's the denominator really? 1 subtracted negative x. So that's what it looks like. First term is 1, multiplied by negative x, negative x. Multiply that by negative x, positive x squared. Well, suppose I want this. See, this is what we're working off of. 1 over 1 take away x is the parent of this. So we change this to 1 plus x, which alternates the signs. And I would say, based on that, do x over 1 plus x. Let's just going to multiply everything by the numerator. This series on the right estimates that function on the left in the interval of convergence. What is the interval of convergence for that problem? The interval. What are you multiplying by? Yeah, you're multiplying, right? So the absolute value has to be less than 1. So negative 1 to 1. Do you recognize that? No, you don't. So look what happens. Nobody expects you to recognize it. The derivative of the left side. So the derivative of this equals that. There's the work. derivative of 1 over mu, or I'm sorry, mu to the negative 1, gives you negative 1 mu to the negative second times d mu, so the negatives multiply to 1. Yes? Except now look what happens. If you took the derivative of the left, just take the derivative of the right. See, we agree that this is true. We agree that this is the derivative of that. So we just differentiate both sides of the given, and we would get this can be represented by that series. So we're going to stop the PowerPoint and go back to the PDF. There's where we were. Yes? So let's look at this. Let's just take a look at this one first. Let's go over problem 68. Where's that going? Huh? Correct. C is the answer. Yes? Because the constant multiplier is 1/3. You have the first term over 1, take away 1/3. 1 divided by 2/3 is 3/2. It equals 3/2 as long as you never stop adding terms. This is an example. Ready? When x is less than 1, 1 over 1 take away x, where the constant multiplier is x. So I build my H chart here, which is a big deal. Don't skip stuff. The 0 term. You're starting the 0 term because you're going by this subscript here. Start at 0. The 0 term is x sub 0. Anything 0 power is 1. So my sum is 1. Next term, x to the first. So I add diagonally, or straight down vertically, 1 plus x. 1 plus x squared, which is that, because x to the 0 is 1. So what did I do? I went to the calculator, and I put 1 over 1 take away x in y1, and I went out to x caret 7 to see how good the estimate is. Except you got to be careful. I made the delta x 1/10, because this only works when the absolute value of x is less than 1. So you can't just like, oh, I pushed, it doesn't work because I looked at my table. If your table set is 0, 1, it's not going to work. It works between 0 and 1. So here's example 4, which was on the PowerPoint. This we're familiar with. The derivative of the left side equals that. And that is the representation, that's the series for the derivative based on differentiating those terms one at a time. So I'm just leaving it up there. That's from the PowerPoint, and you're going to two problems, 21 and 27. All I did was build the H chart. The constant multiplier is 2x. So 2x, the absolute value of 2x has to be less than 1. How do you do that? I have the absolute value of 2x is less than 1. To get rid of the absolute value symbol, you go from negative 1 is less than 2x is less than 1, and then you divide everything by 2. And that gives you x is less than, I'm sorry, x is greater than 1/2 and less than, greater than negative 1/2 and less than 1/2. That's your interval. What does your H chart look like? First term would be 1. 2 caret 0 times x caret 0. Then you multiply that by 2x. You get the next partial sum, which would be 1 plus 2x. Then term 2 would be 4x squared, which is 1 plus 2x plus 4x squared. So if you are at home, you are dismissed to do the exit ticket. We will see you in the building on Thursday.